Thank you very much. I first want to thank the organizers for their hard work and paying so much attention to details. This is one of the most best run conference I've been to. And I really was hoping to attend in person, and it's a pity that this cannot happen, but I hope sometime in the future, near future, we'll be able to gather, discuss. That would be really lovely. So let me share my slides. I hope this works. So let's see. Here we go. Now, unfortunately, I'm not able to see anything in chat. So if you have any questions, feel free to interrupt me or just shout out questions. I think that would be more appropriate in the informal discussion style of what this workshop, of course, intends. So I'll talk about some rather strange topic, which on the one hand is way too simple to talk about. On the other hand, it's a little too technical to talk about. So it's at the same time shares both of these components, and as we go, you'll see what I mean. But in part because it's somewhat esoteric, I want to make sure the idea or what I'll be discussing is clearer from the beginning. So I'll explain it in the most basic terms. So in quantum topology, we often construct invariants of topological objects in 3 dimensions. That would be 3 manifolds and nodes and links out of basic algebraic ingredients. So in technical terms, this could be modular data, R matrices, things like that. But these algebraic objects usually come from completely different field. For example, they can describe symmetries of integrable lattice models or vertex operator algebras. And this interplay between algebraic ingredients providing fuel or basic building blocks for topology is what we usually call quantum topology. So this talk is going to be about asking what happens if these algebraic structures that provide the fuel for quantum topology in turn have symmetries themselves. So it's a situation where symmetries have symmetries. And I want to point out that most traditional ingredients, for example, construction of Witten-Reshetikhin Turaev invariants and close cousins, does not have this feature. So in that case, you don't have any symmetry. So this question appears sort of at the next chapter in quantum topology. And that's why we usually don't learn about these things in graduate school. But nevertheless, such things appear. And that's why today I'm going to talk or try to kind of put it all together, what happens to structure of TQFTs when we have symmetries. And stepping back for a second, again, in the usual context where algebraic structures provide ingredients for building topological quantum field theories, these symmetries of integrable lattice models, they may have different names. Some are quantum groups, and of course, this is more traditional for constructing quantum invariants. Some are Youngians, and likewise, you may find many other infinite dimensional algebras. So here I'm becoming gradually more explicit. For instance, these algebraic structures, I'm giving them names such as quantum groups, vertex algebras, or MTC stands for modular tensor category. And one of the highlights in this sort of interaction or bridge going from algebra to topology is a famous theorem of Turaev based on Reshetikhin Turaev construction, which says that if you give me modular tensor category, it has all the data that's sufficient to build a fully fledged 3-dimensional TQFT. In the context of extended TQFTs, this MTC should be understood as a category associated to a circle, and this aspect will feature later in the talk in a certain place. Another highlight, for example, is of this interaction, this bridge is Verlinde formula, which says that modular matrices and modular data of vertex operator algebra can be directly used to learn something about dimensions of vector spaces that TQFT associates to codimension 1 space, namely 2-manifold. And as a result, partition function on S1 cross sigma G is nicely expressed in terms of such S matrices of SL2Z representation that comes from either VOA or MTC. And of course, there are many relations of this type. So what we're going to do in this talk is to ask what happens if these algebraic structures themselves happen to have symmetries. Namely, what if VOA has a symmetry or MTC has a symmetry? What if quantum group or anything other than this algebraic structure has a symmetry? Then of course we would expect that TQFT should have a symmetry, and question becomes, how does it play with cutting and gluing? What happens to Rive's theorem, or what happens to Verlinde formula in the presence of G action? So as you can anticipate, something will naturally become equivariant, and again, this is not supposed to be super complicated, but surprisingly, things get quite tricky and interesting. And it's this interplay that I want to discuss today. So in particular, here I should, returning even to this slide where we talked about Verlinde category, WZW models, and Richidichian to Rive invariants. In this usual setting, the quantum group which we use doesn't have any symmetries, or the usual WZW model doesn't have any symmetries. But if you look at restricted quantum group at the root of unity, that actually has a symmetry, that has a group of automorphisms, and that's what I mean by symmetry of the quantum group. It's a symmetry of its representation category, or equivalently, a group of automorphisms of quantum group. The corresponding MTC and VOA in this case also has a symmetry. It's not WZW anymore. So this correspondence, which usually goes by the name of Kazhdan-Lusztig correspondence, associates to restricted group sum VOA, which is not quite rational VOA that we usually encounter in this context of Kazhdan-Lusztig correspondence, but it's logarithmic vertex algebra. That's a more interesting beast. And part of the reason it's more interesting is it comes with automorphisms, namely with a G symmetry. And the corresponding TQFT, which is associated to this by Turaev type theorem, which is in fact construction due to Blanchet, Costantino, Gir, and Patura-Miran. So I'll abbreviate this later in my talk as BCGP. So the corresponding TQFT also has symmetries, and this plays a rather important role. So one of the goals is to describe what this gentleman did in a slightly different language, trying to put this subject in a framework that fits well with many other instances where symmetries naturally appear either in quantum groups or in vertex algebras or in TQFTs in such a way that everything sits under one roof, and there is an easy way to go from one to another. So there are many instances where similar structures have already appeared. For example, there is a whole subject which became very popular recently in studying phases of matter in physics that goes under the name of G-crossed modules. So their G is the same G. It refers to the symmetry of the system, and I'm going to use it in exactly the same way. And their language is quite different from BCGP. Likewise, in the study of fluor homology that we already saw in several talks so far, we know that additional structure is required under the name of spin C structures. And there we also face a question of cutting and gluing in the presence of these additional decorations or structures, which again, on the face of it, looks very different. But if we think about Higard-Fleur type problems associated to quantum group of GL11, then again, it's a natural question how to bridge this gap or description of these decorations with the ones used in these other subjects. And one attitude could be that we don't need to bridge them. That's fine. They each have several different incarnations and different descriptions. But I think building bridges is a good idea. And actually, in the problem that we were facing with Francois Costantino and Pavel Putrov, we actually were kind of forced to explore relation between these different decorations or different additional structures. So to us, this question was unavoidable. And what I'm going to do today, I'll describe for you a tiny part of this work. So unfortunately, or fortunately, I'm not going to go in details of this somewhat lengthy papers, but I'll show you a couple of theorems, mostly from section 5, which focuses mainly on these decorated structures, how they play along in different forms and relate different looking TQFTs. So that's the main goal. Maybe I should pause for a second if there are any questions so far. This was a very gentle introduction. I apologize if it quickly became too technical. Okay, so then moving on. Many people here are interested in categorification, and actually that was our motivation as well. So I'm not going to repeat something that many of you probably have seen before, but to make this talk self-contained, I'll put a couple of slides on what the goal was. So here I already sort of touched non-semisimple TQFT a little bit, and again, some small aspects of it we'll see later in the talk. But the other part of my title and also title of this paper is a Q series. So motivation here comes from attempt to categorify three manifold invariants, namely Witten-Reshetikhin-Turaev invariants of three manifolds, where one would expect that just like Hovanov homology categorifies the Jones polynomial, you should be able to express Witten-Reshetikhin-Turaev invariants at some level k. That's parameter of the quantum group at kth root of unity. In terms of graded dimensions of some homological invariants associated to a three manifold, and here ... refer to all kinds of details or coefficients that you could put in, but question is how to get this sort of categorification or homological invariance. And many people have thought about this problem. In fact, many people in this room. And one of the first challenges that we're facing is that Jones polynomial is presented to us in a very nice way, basically as a polynomial on Q with integer coefficients. And therefore, the workforce goes into categorifying these integer coefficients. In the case of WRT invariants, unfortunately, that's not the case. And WRT invariants of general three manifold don't seem to have any nice expression in terms of variable q, which is exponential of 2 pi over this integer level. So q is a root of unity. And it's in terms of the level k that most formulae are generally written. For example, here I give a very explicit form of WRT invariant for a family of three manifolds. You can probably guess what it is, and I'll come back to this formula later in the talk. And you see that here K appears in a few places. So it appears under the sign, which is not so bad. You can write it in terms of Q, that's okay, albeit fractional powers of Q. But what's a little worse is that K appears as overall power here, or upper limit of the sum. And this, of course, if you try to write in terms of Q, you'll get log of Q appearing in random places where you don't want to see it. So that's basically the challenge. And this problem was approached or is approached in a number of different directions. So there are many different avenues which are currently being explored. So one is based on topological algebra. This is a nice mix of Hopf algebras and homological algebras at roots of unity, where basically root of unity controls the length of the sequence, and you study analogs of acyclic complices where differential pth power or kth power of differential is 0. So many of you know the subject well, and I think Josh is gonna talk precisely on this topic. Another approach to this problem is via high representation theory. Again, this has been mentioned even in the talks yesterday. And in this talk, I'll focus on a slightly different approach, which tries to take these values at roots of unity and extend them inside the unit disk to a holomorphic Q series such that coefficients of this Q series are integer. So that's that would be the analog of the Jones polynomial that later one can hope to categorify. So the goal is to re-express this messy looking answer in terms of Q series with integer coefficients. And I would expect that all of these techniques should be combined and hopefully related. In fact, it's the joint strength of them that will be needed at some point later in this talk. So again, I'll come back to topological algebra in particular. So in trying to construct this Q-series invariance, so based on physics, which is analogous to physics of physical interpretation of Hovanov homology and Hovanov-Rosansky homology, one can come up with a candidate. And funny thing is that this candidate is not a unique Q-series. So yes, you get homology groups which are doubly graded for a 3-manifold, and this Q-series is basically graded to a characteristic. But surprise, at least to me, was that it naturally predicts that such objects should be labeled, should carry additional labels B. So this B originally was identified as element of the first homology and later clarified to be a spin C structure. So first, this appeared in our work with Ciprian, and then in paper with several other colleagues, including Posheng Singh, Hirako Nakajima, Park, Pei, and Sapenko, we gave an alternative perspective via Rosansky-Witten theory, where the role of spin C structures is again relatively easy to see. But at first, this was quite surprising, quite mysterious. And surprise was basically at 2 levels: why this additional structure show up in the first place, because WRT invariant does not depend on anything other than choice of root of unity and the root system, and of course the underlying manifold. But in the case of this Q series, it seems that this does require something additional. And in the spirit of this talk, I'll call this something additional a decoration. So that's going to be part of decorated TQFTs. And once this H1, which as I said is the same as spin C structures, but of course it's non-canonical isomorphism here. So once it was understood to be related to spin C, question became even sharper in the sense that whatever the Z hat is, it's clearly becoming spin TQFT. So in other words, it's requiring spin structure, whereas WRT invariants don't require spin structure. So it's a little bit interesting and curious where this spin structure is coming from. And of course, there is no contradiction, because to get WRT, you would basically have to sum over these additional labels and sum over spin structure. So it may totally disappear. That's probably fine. But nevertheless, at least to me, it was quite interesting and puzzling why this extension inside the unit disk suddenly requires a dependence on spin structure and becomes a spin TQFT. So, right. So as a last point about this holomorphic Q series for generic values of Q, in that paper with Ciprian that I mentioned very briefly, we proposed a surgery formula, namely how to construct it for surgeries on knots. And that surgery formula was for negative definite surgeries, roughly speaking. So this was extended to positive definite surgeries recently by Park. So he proposed an analog of this formula. And moreover, one needs to construct first this Q-series invariant for knot complements to perform a surgery. So with Ciprian, we managed to compute one infinite family of torus knots and one hyperbolic knot, namely figure 8. So it seemed pretty laborious, because at least by the techniques that we used, but recently Park used R metrics applied to Verma modules for quantum group a generic value of Q, which of course is what one should expect, and managed to produce a very efficient computational scheme that allows to compute this for many knots up to 10 crossings, and again with both plus surgeries, minus surgeries. And here is an example of +5 surgery on some 10 crossing knot, which has therefore 5 possible spin structures, and as a result you get 5 different Q series. So that's a very explicit expression. As you can see, all coefficients here are integers, so that's supposed to be the starting point for categorification. So the problem we were facing with Francois and Pavel is relation of this kind of invariant to various other invariants. And if we speak of geography of decorated TQFTs, roughly here is the summary. So in the unit disk, you have this kind of Q-series invariants labeled by spin C structures. As Q goes to roots of unity, you can reconstruct more familiar invariants. They include WRT, that was original motivation. But then it was quickly realized that, and hints for this we're seeing before, that much more natural connection is actually to so-called logarithmic or non-semisimple invariants that we mentioned earlier. Because at the level of quantum group, connection to WRT involves 2 steps, taking Q to root of unity and semi-simplification. But this step of semi-simplification is actually not quite natural. And as a result, connection to ADO invariants and BCGP invariants, remember this is for Christian Blanchet, Costantino, Gear, and Patura-Mirand, is actually more natural. So I'll tell you a little bit, well, one tiny bit about this theory, this non-semisimple logarithmic theory. One important thing is going to be that it will be going to be important in the rest of the talk is that it's also decorated. So just like this invariance and the unit disk inside the unit disk are decorated by spin C structures, this one is also decorated, and usually the decoration in the world of BCGP is called omega. I'll come back to it a bit later. And it's an element of H upper 1 with C star coefficients. And here I'm omitting some details for sake of this presentation. For example, this decoration is not allowed to be 0, and so on and so forth. So experts know this. Non-experts may consider this not terribly important, at least in the first run. So then at various other roots of unity, you can find either Toriv torsion, which is also labeled by spin C structures, or Rochlin invariant, which is labeled by spin structures. So everything that you see in blue on this slide is referring to this additional structure, or as I'm going to call it from now on, decoration in TQFT. So question therefore becomes is A, how to put many of these things under kind of one roof, and also B, how on Earth can one type of structure become another type of structure in a way that's consistent with cutting and gluing. So at a technical level, that's precisely the question I'm trying to ask and partially address. So I'll come to the kind of main part of the talk, or this is the gist of this this talk. Again, if there are any questions, feel free to ask now. What I'm going to do is to actually describe a formalism that will be applicable to any d-dimensional TQFT that I'll call decorated TQFT. Of course, interest is in 3 dimensions, where I already showed you examples of such structures, but maybe if time permits, toward the end, I show even 4-dimensional theory where such things appear. So if, again, there are any questions, feel free to ask.
So may I ask a question? Do you hear me?
Exactly. Yes.
So your geometry is concentrated only on this left or right rectangle. So how about other rectangles? So how about angle which is more than 90 degrees and so on? So you only consider roots of unity which of the 4 exactly. So how about, for example, q going to q minus 1 or something which is
well, here I illustrate this picture omitting q equals -1 for presentation's sake, but actually you're right that much of these relations were studied in this kind of rectangle, and there is definitely q equals -1, q equals I, and also q equals 3rd root of unity are rather special, and that's actually where one finds deeper structures and connection with more interesting cobordism invariants. They haven't really been studied as much as I think they deserve. So yeah, I think it's a good question. But did you have something specific in mind, or if it's a general question, I certainly agree. Yeah. And probably there are many other questions one can ask. Even at the roots of unity, for instance, it turns out that if one sums over spin C structures, one gets WRT, as I mentioned before. But if one doesn't sum over spin C structures, but tries to keep some of this additional information, which is going to be our friend, hopefully by the end of this talk, then one can recover this BCGP and other invariants, which are also decorated in one way or the other. To me, honestly, these decorations were at first a nuisance, and then they became part of the structure that seems to appear everywhere. So that's part of the reason for giving this talk, just so to face my fear, if you wish. Okay, so we'll need a slight generalization of notion of asymmetry, which in mathematics goes under the name of gerb. Just like usual bundles are classified by studying maps from our manifold into classifying space BG of some group G, you can study maps into higher classifying spaces B to some power of G, and this would give you what's called n-gerb. Luckily here, we won't be needing any of this technology of gerbs. We'll talk only about flat gerbs, and connection on a flat n-gerb is n+1 form. In other words, if you have a usual line bundle, which is 0 gerb in this sense, connection is 1 form, and its corresponding holonomy or data is classified by h_1 of our d-dimensional manifold, if TQFT lives in d dimensions, with G coefficients. So for me, G will be abelian from now on. In fact, I should have mentioned this earlier. So when I talked about restricted quantum group having symmetries, restricted quantum group actually has non-abelian symmetry group. But I'm going to focus only on Cartan of that symmetry for a number of reasons. So one of the reasons actually is visible already on the slide, because theory of gerbs only is reasonably well developed or exists for abelian G. So I'm going to restrict myself to a billion G from now on. And later there will be several other reasons which will make the story a little easier to describe when G is a billion. You'll see why. So I'll refer to such symmetry. Actually, this is not my term, but something that's, again, actively used in the study of SPT phases and condensed matter physics, N-form symmetry. So the reason it's called N-form symmetry is that if you think about this A as a gauge connection, the gauge transformation is by D of N-form, and therefore N-form becomes the parameter of this gauge transformation in such context. So therefore, we'll be studying, in general, D-dimensional TQFTs and such higher form symmetries associated with abelian groups. The question is, so on a closed D-dimensional manifold, this data requires a choice of element of H upper n plus 1 with G coefficients. And first question we're going to ask is how to describe cutting and gluing in the setup when this additional decoration is needed. Well, let's specialize to the case D equals 3. Again, many things will be easily generalizable, and I'll state the general result later on. But for D equals 3, which is more relevant to three-manifold topology, you can quickly figure out what this Hilbert space associated to sigma should look like. Basically, what should be the generalization of Ati's axioms when you have such G action. And the way to think about it is to consider a special case when, so Hilbert space should be associated to some surface sigma. So we should take a manifold, three-manifold, to be sigma cross S1. And as we mentioned earlier, for example, in the context of Verlinde formula, the partition function or invariant of sigma cross S1 basically computes the graded trace of this Hilbert space. So we want to take this invariant on sigma cross S1. We know that it will be decorated by holonomies H upper 1 of sigma cross S1 with G coefficients. But now we want to rewrite invariant of sigma cross S1 in such a way that it can be presented as a trace over the Hilbert space associated to sigma, possibly graded by some additional data. Well, if on a three-manifold our decoration is element of H upper 1 of M3 with G coefficients, then surely restriction of this data, which I'll call omega, that's again the notations that BCGP used, will be also restricted to sigma and will provide some decoration of H. That's kind of obvious. That's what I'm going to call decoration. So therefore, we already know from the start that H of sigma is decorated by H upper 1 of sigma, just like on a general three-manifold, invariant is decorated by H1 of a three-manifold with G coefficients. But then by doing the simple computation based basically on Kuhnert theorem and relation between homology and cohomology, you want to express the term of H1 of sigma cross S1 coming from a circle as home of something into U1, such that when we take the graded trace over the Hilbert space, that something becomes the additional grading. And if you go through this extremely simple calculation, you find that the something is nothing but H upper 2 of sigma with coefficients not in G, but rather in a Pontryagin dual. So this is, again, some simple computation, but it has an important lesson because this is first time where a Pontryagin dual shows up. And the goal of this talk is to describe operations on TQFT, which in particular, among other things, will involve replacing G by its Pontryagin dual. So that's going to be important. So in other words, if I were to give more actual title for this talk, it would probably be duality for 3D TQFTs, where by duality I refer duality between G and G check or hat, where G hat is the Pontryagin dual. So in particular here on this slide, it shows up as grading of our decorated TQFT in a different degree. Original degree was H1 because this was the usual symmetry. And again, that's going to be relevant to BCGP. But if you want to encode, not to lose information that we have under cutting and gluing in such setting, and somehow encode the orthogonal direction, orthogonal to sigma, intrinsically in terms of sigma, we have to use opposite degree. So 1 becomes 2, and we have to replace G by Pontryagin dual. That's the upshot. So this looks kind of esoteric and abstract, but actually, if I take the simplest possible quantum group, I mentioned quantum groups earlier, and I'll come back a number of times to these examples. So let's just take a billion group, and again, choose K to be some integer, so Q is a kth root of unity. So this is basically WRT invariant for U1 at level K. This theory, even though it's extremely trivial and it's invariant for a 3-manifold as a Gaussian sum, and invariant of knots and links is Gauss linking number, no pun intended. This theory actually has, despite it's a simple kind of invariance, it has precisely this U1 symmetry, which is in this notation zero form symmetry. It could be U1 or C star. Everything will be algebraic, so we can consider it over any field. Important point is that you can introduce these decorations exactly the same as in BCGP. Namely, you can enrich this theory by element of H upper 1 of your 3-manifold with U1 or C star coefficients. And if you want to ask how is cutting and gluing done here, we'll discover exactly the same decorations and gradings on the Hilbert space. I'll call them slightly differently to distinguish that decoration is simply restriction of decoration from ambient n-dimensional or d-dimensional TQFT, but grading involves this interesting step that replaces symmetry by the Pontryagin dual. And in the context of this Chern-Simons TQFT with abelian gauge group, you can think of the symmetry simply as something that couples to C1, the first Chern class of the line bundle for the gauge group. So you take basically dA, the curvature of the gauge connection, which we are integrating out in this Chern-Simons theory, and multiplied by omega. So that's going to be exactly element of H upper 1 of our 3-manifold with U1 or C star coefficients. So that's obvious from the way it's written, and that becomes the decoration on a general 3-manifold. But again, this is what you find for cutting and gluing of vector spaces. So again, this is basically extremely simple, but as you can see, it's already becoming somewhat esoteric and interesting, and even in the simple example. So if we talk about, so here I talked about invariance of 3-manifolds, Hilbert spaces in the presence of such symmetry. What about the category? So the category, as I mentioned earlier, is something that extended TQFT should associate to a circle, and it basically tells us about category of lines. These are the lines for which we compute Jones, Khovanov, and other invariants. So therefore, these are our favorite braids and tangles that live in a 3-dimensional space. So here, the category in this case of quantum group based on at U1 at that root of unity can be considered as a sum of categories, each of which has k-simple objects, which is not surprising if you work at quantum group of U1 at level k. But what's interesting is that the sum is labeled by elements of our G, which in the present case is U1 or C star. So in fact, for any choice of G in U1, you get a copy of this category, which again always has k-simple objects, but they are slightly different in the sense that the charges or representations of this U1 lines are shifted from integer values. So for G equals 0, these are the usual ones, but when G or G equals 1, but when G is not equal to 1 as a group element in this U1, then these representations are shifted away. and they're kind of illegal. So their highest weights are not integer, but integer plus some fraction. And in physics, so such things are represented not by line operators which exist on their own, but by line operators which are attached to the boundary of a surface operator. So a surface operator is something supported on a surface in three-dimensional space. And for G, which is not equal to 0, 1, depending again on the convention, we necessarily must attach such surfaces to lines. So here there is an interesting lesson that if you are to study such more general categories, by the way, this is what I'm describing. Some of you who know G-crossed modules, that's exactly the G-crossed module. So in general, one needs to study basically tangles or braids with the surface operators. And that's something that may be interesting or useful, perhaps for developments, including foams and other things in cases where Q is generic or such symmetries are present. So what I described in the simple example holds true in general, and I'll gradually try to reformulate it in such terms. So we have a category which is splits as a sum over elements of G. And here actually I'm using again the fact that G is abelian in a crucial way. If G was non-abelian, the structure would be similar, but it would involve sum over conjugacy classes. So when G is abelian, that's the same thing, but things would be much more complicated if it's non-abelian in this formula as well as in the fusion. So fusion here is such that if you have pieces of this category or G-crossed module associated to elements G1 and G2, and you try to fuse them, for example, lines or tangles with different labels, then labels simply multiply. And the way to think about them is that in 3 dimensions, our lines not just carry representations of a quantum group, but they carry holonomy around it. And when we fuse them, of course, holonomy multiplies. Holonomy for this G symmetry. And again, we think about this decoration as flat connection and the complement of this setup. So in 3 dimensions, this looks already quite interesting and non-trivial, but people in vertex algebras who studied this setup via Kazhdan-Lusztig correspondence have seen this all along. In fact, even the fact that something should be attached to this line operator is quite visible on the boundary under the name of twisted sectors. So therefore, the slogan or dictionary is that what we're discussing here under the names of decorated TQFTs, G-crossed modules, and things like that is nothing but incarnation of twisted sectors in vertex algebras, which are related to these categories via Kazhdan-Lusztig correspondence. Okay, this was kind of warm up. This was usual symmetry, and you already see that story gets quite interesting. So let's look at something slightly more esoteric. I said that G can be any abelian group, so let me take it to be Z, the integers. And now I'm going to consider decorations by not the usual symmetry, which suggests that I should pick background from H upper 1 with G coefficients, but now I'm going to take H upper 2. So in this previous notations, this is more exotic symmetry called one-form symmetry. So its connection is a 2-form, and the corresponding holonomy is H upper 2 of whatever we're studying with Z coefficient or G coefficients. Following the same calculation, again, based on Kuhnert formula and relation between homology and cohomology, you quickly conclude that these labels, I'm going to call them suggestively B, on sigma cross S1, first of all, can be obtained, come from restriction of the decoration from 3 dimensions to the surface sigma. But the P is coming from S1, you can re-express nicely as hom of something into U1, and this something now is H lower 1 of sigma with Z coefficients, or equivalently H upper 1 of sigma with G hat Pontryagin dual coefficients. So summarizing what we discussed before, the previous case, kind of the usual symmetry, you find that Hilbert space is decorated by H upper 1 and graded by H upper 2 with Pontryagin dual coefficients. Here, in this case of more exotic symmetry, where a degree is shifted, you find that similar pattern and naturally degree is shifted. So that's maybe not too surprising. What's interesting is that these two cases I discussed are precisely the ones which are relevant to BCGP invariants and Z-hat invariants, where in one case symmetry is U1, in the other case the symmetry is in a different degree and is actually Z. So as you can see, in such situations, H sigma, following the rules that we just walked through, you see that decorations and gradings are exactly the same if you swap them. So here you have H upper 1 with U1 coefficients, H upper 2 with Z coefficients, and here you also have H upper 2 with Z coefficients and H upper 1 with U1 coefficients, but the role is completely swapped. So you probably can anticipate what I'm gonna say next, especially since I already announced that we're looking for connection between this BCGP and Z-hat invariants. And for this, I'll need, so I'll introduce now something more non-trivial, an operation on TQFTs that allows you to start with TQFT that has symmetry G and construct a new TQFT. So here is an interesting statement. Take a TQFT with a symmetry G, which can be any n-form symmetry in our previous notations, and simply divide by this symmetry. This is what's usually called gauging or bifolding of TQFT. So you get a new one, and claim is that this new TQFT will have also a symmetry, which will be precisely the Pontryagin dual of G, and it will sit on some other degree such that its decoration will require choosing element of d minus 1 minus n. So that's a theorem. And at the level of invariance for closed manifolds, this operation, or in constructing invariant of TQFT modded out by G, is simply a Fourier transform with respect to G. So let's think about G as a discrete group for a second, say cyclic group for simplicity. Then invariants on closed manifolds are just obtained by summing over all these background connections n+1 forms on MD, and that's of course what gauging should be, or bifolding should be. And in the process of the sum, you may introduce a factor which involves composition of the Poincare pairing with the pairing between G and the Pontryagin dual, which is this exponential factor. So the result in general actually may depend on analogous background or decoration B, which valued in degree d minus 1 minus n. This follows immediately from Pontryagin duality or Poincare duality. At the level of Hilbert spaces, we already saw what should happen, namely we should swap the gradings and decorations. We saw it in a particular example of BCGP and Z-hat, but this is actually true of any theories related by this discrete Fourier transform. And a theorem, which is perhaps the most non-trivial part of the statement that we prove in a paper with Francois and Pavel, is that you can extend this to cobordisms. For example, if G is finite, this does not require any assumptions. But in case when G is U1 or Z, in this Fourier transform, you'll have an infinite sum. So you need to do a little bit of additional analysis that guarantees convergence. But theorem is that if convergence is present, such as for discrete G, for example, then this also extends to cobordisms. So this is actually a statement about full-fledged transform, Fourier transform that relates TQFT with a symmetry G and TQFT with a symmetry which is Pontryagin dual that sits on a different degree. And now you can see why I had to go through all this song and dance, because we could, of course, describe TQFTs with symmetry as usual, more standard technology. But the point is that the dual symmetry would live in the wrong degree. So I had to introduce this notion of generalized symmetries to even talk about it. Another theorem, which is actually much simpler, this is more like a lemma, is that if you repeat this operation of orbifolding or gauging twice, you get the original TQFT. And this basically is analogous to the simple fact that if you apply Pontryagin duality twice, you get back the original group. So that's very simple. So coming back to what we were handed over as a homework problem, we knew already that invariants at a numerical level for three manifolds are related. So you can take the z hat invariants and q to root of unity and recover this NR invariants. These are CGP invariants if you sum with some universal simple coefficients, and then the gradings, I mean, this spin C structures in Z hat become decoration omega. So here I'm sweeping under the rug one last ingredient that I'm basically replacing spin C data by H upper 2 decoration in my previous discussion. So they differ by choice of spin structure, and part of this operation also gets rid of the spin structure. So that I'll sweep under the rug in view of time, but again, you can find details in the paper. There is nothing really subtle or delicate about it. So this is just additional complication, but everything works through, and you can basically prove that you can convert spin C decorated TQFT into H upper 1 C star decorated TQFT, which is what BCGP is. So it works at the level of Hilbert spaces, at the level of cobordisms, but there is one ingredient which actually struggles to extend to cobordism. So we have almost a proof of this relation, and it involves so-called R-wrapping. So when we take Q to root of unity, you need to perform reduction mod R in some Hilbert space. And this is something that we managed to show at the level of one extended TQFT, namely to get it to the level of Hilbert spaces. But with cobordisms, we have almost a proof. It's not quite a theorem. And if anyone is interested in further questions or topics for future development, this was obviously one of them. And I believe this is where connection to topological algebra could be helpful, because questions like this precisely is something that's naturally appearing in topological algebra. So I suspect that there is a lot to be learned in here. So what's the problem? The problem is that, and I'll conclude in a couple of minutes, so I apologize. We started a bit late, so I'll take 2 more minutes if that's okay. So in earlier slides, I showed you that in WRT, in fact, this was our example of 3 manifolds where WRT is given by a sum and so on. And now I want you to pay attention to the sum. So sum is precisely obtained from taking a trace over Hilbert space, and it runs over integers, basically from 1 up to k. K is the level, and here, of course, we assume that it's SL2. Analogous formula for this z-hat invariance involves either integral and integer sum, or if you use Fourier transform, it would be sum over 2 integers. So when every time you glue 3 manifolds along tori in WRT world, and BCGP is very similar, you get one-dimensional sum over single integer truncated by k. Every time you do gluing over toral boundaries at generic Q, you get double sum, not truncated. The fact that it's not truncated is not surprising. So that's what you should expect at generic for quantum groups at generic Q. But the fact that it becomes 2 copies of the lattice, so here lambda and lambda check stand for root and weight lattice respectively, that's kind of interesting. So this suggests that a generic Q cutting and gluing along toral boundaries should be described by double affine algebras or maybe toroidal algebras of some sort. In any case, for rank 1, this boils down to, again, both are familiar in roots of unity and generic Q. So the first line boils down to this one-dimensional sum up to R truncated, and this boils down to double sum. So when Q goes to root of unity, somehow trace over this Hilbert space, which is this infinite sum, has to become a single sum truncated by R, and this is the nature of this operation that we call R-wrapping. That's a reduction of grading mod R, because the sum, double sum here is in fact not unrelated to the decoration that I discussed before. So as a result, there is this question or operation, which is something we didn't fully address. And again, that's probably something that can benefit from interaction with homological algebra. I was planning to give you a couple of other examples of decorated TQFTs and spin TQFTs, which require this decorations and cutting and gluing. In view of time, I'm gonna skip this, and thank you for your attention.
Any questions?
Or maybe so if I understand correctly, so there should be some kind of decomposition of, say, Jones polynomial of knots in terms of spin C structure of the sum surgeries of over this knot. And so is this in any way computable? So in terms of, I don't know, representation of UQ, so SL2 or something?
So for Jones in the 3-sphere, you don't need this, in part because 3-sphere has unique spin C structure. So that's maybe modern way of or a way of understanding it from this perspective. If you want to compute analog of Jones polynomial in a more general 3-manifold, then yes. So here you can replace M3 by a pair, M3 and then knot or link. And yes, so then everything will be labeled by choice of spin C structure on the MBN 3-manifold in which the knot or link lives. It actually works quite well and agrees with structures that people start seeing in annular homology. So that's a simplest example of knots and categorification inside the solid torus. Yeah. And as far as computable, I guess that's the best technique I can offer. It's mostly being applied to closed 3-manifolds, but techniques exist and allow to do computations, of course, for knots and links and 3-manifolds.
We have another question.
Maybe it is silly. I remember that at some point you have this construction of these invariants for closed 3-manifolds, but they only were mathematically rigorous for clumped 3-manifolds, not for arbitrary 3-manifolds.
That's correct, and that's to some extent still true, but clumped was basically frontier 3 or 4 years ago. So then in paper with Cyprian, we proposed surgery formula that allowed to compute, for example, this invariance on torus knots, figure 8 knot, and more recently, again, Park extended this to many other infinite families. So, and also previously the frontier was only for negative definite clumped manifolds. Now this was removed also by Park. So whenever they're defined, which is pretty large infinite families and many classes, one can check invariance under Kirby moves. So in fact, the invariance under Kirby moves often is easier to check than computing the invariance. So yeah, but we still don't know how to compute this for knot complement of the most general knot or link. So,
Other questions?
Yeah, I have one question. Hi, Sergey. This is Neetu here. Hello. Can I? So you had a very easy, simple example of Chern-Simons, abelian U1 Chern-Simons level K, and you know, we talked about symmetries on that. Can you say anything, at least in that simple example, about the actual categorification, the actual homology groups? Where's the geometry of that categorification? As I understand, you haven't really talked about the actual groups, right? Or how you construct them?
That's correct. So in this, right, so neither for U1 or for any other quantum group related to this landscape of Z-hats and Q-series, so in this talk, I didn't really talk about these numbers or how to compute them or how to categorify them. So this is in some sense also the nature of the previous question. So indeed, I gave you a very quick survey of like cutting edge technology, but didn't describe the computations, and much less is known about categorification. I think at this point, maybe time is right to transition to that question, but most people are still focused on computing this Q-series invariants and defining it for larger classes of nodes, links, and so on. So that's indeed what's ongoing. So in this talk, I focused not on numbers, or even homology groups, but on structure. So it was all entirely about this symmetry, which is on this slide has to do with appearance of this labels B, the discrete PNC structure. So
do you have a speculation at all in any simple example, even what for generic Q, what this categorification might be?
So in this paper with Putrev and Vafa, and also in the follow-up work with Dupay, we give a proposal. So we propose what this graded dimensions should be for simple manifolds such as length spaces, where the answer is already quite non-trivial and relates to McDonald polynomials and other things. And I think in a couple of other examples, simple examples such as Poincare sphere, maybe S1 cross sigma. Actually, using this technique with Rosansky-Witten theory based on a fine Grassmannian, you can produce the answer for S1 cross sigma.
Yeah. And does complex K theory as a cohomology theory ever does it appear in any natural form? I'm curious about your spin C structure. Because that's the natural place the spin C structure would make its presence known.
Yeah, so that's a spin C structure on the 3 manifold. And in that sense, I don't see direct connection with complex K theory or index of Dirac operator, just because we're in a 3-dimensional universe. Wow. But yeah, maybe I need to think more about it. I don't see any immediate connection.
Thanks.
So let's thank the speaker again.